This is going to be a complete solution for Jacob's problem 410. Okay, and remember when you're watching YouTube that you can actually speed things up and slow them down by clicking the gear down here, and it gives us this pop-up window, and from there you can select how fast you want to run the video here, so you can speed it up. Usually you can listen a little faster than the people are actually speaking, and it takes a long time sometimes to get through these problems. You can also go forward and backwards, of course, so you can really get this down. So you should be able to review this, get the whole concept of where we're going with this. So we had the simple form of a critical path model that only had the nominal numbers in there. So that taught us how we can go forward and backward in the network when we draw it and figure out where the slack time is. This problem that we're looking at now says instead of using just a rigid one-time estimate for how long it's going to take us to get through any one of these activities, that there's some probability we can get it done faster and there's some probability that we can get it done slower. So this is an optimistic perspective and a pessimistic. Optimistic is a shorter length, pessimistic is the longer length, obviously. Okay, and you could look at this as possibly the best case versus the worst case scenarios here, but in the middle, if everything goes pretty well, we're going to get the middle numbers here. But this is going to introduce this element of probability that we're going to have to figure out the likelihood of hitting the time that the critical path tells us it's going to take us to go through this. Before we start there, let's summarize where we're headed with this. Eventually, what we want to do is understanding the behavior of normally distributed data, okay? So assuming that this is symmetric, okay? So assuming this is symmetric, for all our problems, we assume that the average or the expected value or the mean is right in the middle of symmetric data, meaning that you can fold this over right along the average here, okay? So this would be your expected value, your mean, or your average, okay? And the nature of this is to say that the probability of all the occurrences up to and including this average is going to be 50%. Half of the probability lies to the left, and half of it lies to the right. And as we start selecting points of interest, moving from left to right, the probability is going to get bigger and bigger, okay? Until we get so far over here that the probability is or is very close to 100%, or we express that as 1.00, okay? So we use this z-table, the z-score table, to be able to take our native data, okay? So our native data is here. We start out with our native data like temperature or days that it's going to take us to do the project. And we have a tool. We have a thing called a z-score table, okay? And I'm going to show you one that I've done in Excel, and it matches more closely the one we have in the book, but yet it's still different, okay? So we're going to show you the Excel z-table here. Let me undo some of these parts of the drawing because we're going to come back and use the sheet in a second here, but I just wanted to place where we were. What's our argument here? We have to understand our motivation. We have to understand that we have a network, we have an expected time through there, and we're going to come up with an average. With that expected time, which is the average, we know that that's the 50% mark, 50-50 shot that we're going to hit that. But when we're predicting and forecasting and trying to run a big company, we have to give the customer a date that's more likely than that so that we can hit it, get paid, and not get penalized. All right? And so there's two different kinds of problems here that we're going to solve. By the end, we're going to see the two different ways to look at this, and they're very, very related. They're almost the same thing. But let's go take a look at that the z-score table. Okay, so if we come over to the z-score table, I created this in Excel. There's a function in here, formula. If I click one of these cells, if I'm just going to click here, you can see that I used the norm.s.dist function, the normal distribution function, and you can take some value in there and it will return to you the probability. Again, understanding we're talking about normally distributed data. Try to draw here. It's not drawing for me at the moment for some reason. Okay, it should draw. Okay, for some reason I can't draw in there. Let me go back over to the other window here. And again, I'm just to repeat, what this shows is we have native data, and to get over to this table, what we have to do is use the z-score function here to get to the table. So z is going to be x, the point of interest. What point of interest are we looking at here to find out what the probability of that happening is? And we're looking at the distance from the mean, and we compare that to the standard deviation. How many standard deviations are we away from the mean? So if our points of interest are to the left, these numbers all over here are going to end up with a negative result here. Z will be negative for any point we look at that is to the left of the mean. Why? Because these numbers are smaller. So just to give an example, let's say that a process takes 28 days. Let's say that our mean is 28 days here. The probability of hitting 28 is 50-50, because we know that the way normal distributed data works is that the probability increases as we move to the right, but we haven't hit the midpoint of a symmetric drawing here yet. And all of this represents 100%, so we know that if we come up 50% of the way up the total scale that we have here, that half of the probability lies there and below. Okay, so the probability of anything up to and including 28 would be 50%. And all these numbers would be less than 28. So if we run, just to give you an example, if we run the numbers through here, let's say, what's the probability of hitting 26 days? Well, it would be 26 minus 28 over whatever the standard deviation is, and we can see that that's going to be a negative number. It's going to be negative 2 over whatever your standard deviation is. So coming into the z table, the negative numbers mean you are to the left of the mean, and the positive numbers means that you're to the right. We're measuring our distance from our point of interest to the mean, and so it does take on a negative number here. It's less than 0 here. Okay, so what we do with this equation is we move from native data into simply a common view of this, because we now use, when we get into the z tables, we're looking at the standard. That word says standard there. This is not easy to write on this. So the standard normal distribution of data, rather than just simply normally distributed data. Okay, we've standardized it by running it through this function, and I've explained where this basically centers it around 0 rather than your mean, and it's the number that we get out of this is in terms of how many standard deviations are we lower than the mean, or how many standard deviations are we above the mean. So it can be negative or positive. All right. Okay, so let's flip back over to the table here, and what I've done is I've created a table that runs from, as this works in your book, the back of your book, you should see this too, is that we can come in here anywhere from -4 all the way up. You can see those numbers are increasing on the left hand side there, all the way up to 4 standard deviations. If I wanted to, I could go much wider than this. I could go to 6 standard deviations, -6 standard deviations here, to +6 standard deviations. You can do whatever you want, but I'm just replicating what you have as Appendix G in the book. Now, in the book, they've laid it out a little bit differently. This is what we're looking at here, is what you would find as more of a standard z-score table, what I have here. Okay, in the book, what they do is they have the numbers, your standard deviations that you enter in with, your z-score. Okay, so you come in with your z-score, and right next to it, it has the probability. And on one page, what they do is they tabulate a little bit differently than this table works, but they'll tabulate all the z-scores coming in, and sitting right next to them to the right is the probability of those. It's just presented a little bit different. So it looks something like, let's use a different color than gold here. Let's just say, so these blue columns would be -4, and they'd be increasing just like this thing does. And then they roll over to the next column, and they continue it, and then they roll over to the next column. And next to them are the appropriate corresponding probabilities of that z-score. Okay, that's how your table in the back of the book works. Let me color that a little bit differently. That's just a shorthand for the fact that the book shows this a little bit differently than this table does. There's orange there or something like that. Ooh, those are pretty ugly colors there. But these would be all the list of these -4 all the way up to 4, the blue, and then the corresponding probabilities. Okay. Okay, so let's carry on. We're going to use this this is where we have to get. Okay, and remember, to enter into this, we need to use z is equal to the point of interest minus the mean over the standard deviation. And we take that result and we come into this table and we do a lookup. Okay, so the number we're looking up is along this left-hand margin here. Okay, and it might include, we might have to take into consideration the numbers at the top, which I'll explain later if we need them. Okay, I'm just going to tune in that formatting there just a tad. There we go. Okay, I just wanted to fix that. I just want to format that. So let's go back to our problem and get underway here. Okay. So let's get rid of these notes, and to get started on this, we need to calculate the expected value of the time it takes to do each of the activities. And we start with this table here. We have optimistic, nominal, pessimistic. What was our equation for that? Well, the equation for that is equal to, I'll put it up here out of the way, is equal to, you take 1A, you take 4 of the nominals, and you add a B, and you divide by 6. That's a weighted average. We're weighting the nominal much heavier. It says it's much more likely that that's going to happen than any of the other 2 points on there. Okay, so that's the function for the expected value for any one of these activities. So if we go through this and we punch through it, let's do A first. So we're going to get 1 plus 3 times 4 plus 5 over 6, and that is going to be 1 plus 12 is 13, and 5 is 18. So you're going to 18 over 6 is equal to 3. And something you should notice here, and we're going to take advantage of this, I did this in class, is if you look at how averages work, we're trying to find the midpoint of a range of numbers. Well, if you look at these numbers here, 3 is 2 away from 1, 3 is 2 away from 5, and they gave us some convenient numbers here, so we could just visually inspect some of these and say, you know what, we have some symmetry going on here. Our optimistic is as far away from the nominal as our pessimistic is. And so the activities for which this holds would be this one, where 3 is right between 1 and 5, B, where 2 is right between 1 and 3. Again, same thing. 2 is right between 1 and 3. 3 right between 2 and 4. But here we have, we're going to have to calculate this one, because 4, it's a shorter distance to your optimistic, and it's a long distance, a distance of 7 over to your pessimistic view. Okay, so we're going to have to calculate that. Try to put a C in there. Okay, so we're going to calculate that. Here we have 4 right between 3 and 5, so that we know that the expected value would be 4. We don't have to go through all the calculation there. 4, we have 3 difference to 1, but we have 2 difference to 6, so we're going to have to calculate this. And here we have 4, which is 2 away from 2, but 1 away from 5, so we're going to have to calculate that one. Okay? Alright, so let me start a chart over here. Okay, so the ones that we called out that are symmetric, and so we could do the simplification or shortcut on, is A, the expected value here, or the mean, is going to be 3. It works for B, which is 2, C, which is 2, D, which is 3. E we have to calculate, so it's going to be 3 plus 4 times 4 plus 11 over 6, so that's 3 plus 16 is 19, plus 11 is 30, so 30 over 6 is equal to 5. So our expected value here is 5 for E. We just calculated that one. We had to calculate that one. That's E. Did I point to the right one? E. Okay, so we had symmetry for activity F, so 4 is right between 3 and 5. The average is going to be 4. G, we did not have symmetry. We have to calculate that. So that is going to be 1 plus 4 times 4 plus 6 over 6 is going to be 1, and 16 is 17, and 6 is 23. So we have to go calculate that out. Let's go over to the calculator and get that. Here's our calculator. So we're going to take 23 divided by 6 equals 3.833. Okay, 3.833, and we'll put it over here. That was for G. 3.833 was the expected value there. And we have to calculate the next one again. So that would be 2 plus 4 times 4 plus 5 over 6. And we end up with 2 plus 16 is 18, and 5 is 23 over 6 again. That's just use what we did up here. 3.833, so we have another 3.833. Okay? All right, so now let's draw the diagram, the network. Okay, so let me shorten this up. Let me make this a little bit smaller. I need a little bit more room here. Okay. Okay, so the network says A has no preceding activities. There's A. B has no preceding. Okay. C has A preceding it. Here's C. D has A preceding it. There's our D. E has B preceding it, so this is E here. You should be able to do this. You can shut the video down, and actually you should work this out on paper and then come back to the video. Okay, so it's C, D, E. So C depended on A, D depended on A, E depended on B, E depended on B right there. Okay, so F depended on C and D. Okay, C and D, there's F. G depends on D and E. There's G. And then H depends on F and G. Okay. So that's our network. Now what we have to do is plug in these numbers up here in this previous slide that we got. Okay? And we have to figure out what the critical path is. So I kind of drew it a little bit tight here, all right? Let's see if I can do something about that. And make that a little bit bigger. There, we'll make it bigger. I just grouped them together, and now they're treated as one. I think I needed that much room. Okay, so we can put in, just by inspecting our numbers up here, we can get some of the numbers really quickly, because A is what, 3? Okay, so A had 3, B had 2, that took 2, C took 2. Remember, these were the quickies. These were the ones that were very symmetric here. D was 4. I'm going to put the 4 right in the middle of the D there. That's 4. Okay, and E we had to go figure out, which was, what was E? Let's go back to E. And E was 5. Okay. I'll put 5 in here. And then F was 4 because it was symmetric. We don't have to do any calculations on that. We can just inspect it and say, oh, okay, that was 4. And then both G and H were 3.833. Okay, so let's find the critical path here. So we have 4 paths. We have 1 up here, 2 goes through here, 3 goes through here, and then 4 is the bottom root. Okay, so let's do the top root here. 3 plus 2 plus 4, so 3 and 2 is 5, 9 plus 3.833 is 1. We'll just put the numbers in here. These are the 4 roots. The first one is going to be 9 plus 3.833 is going to be 12.833. Okay. Now we'll do A, D, F, H, and that will be 3 and 4 is 7, and 4 is 11, will be 14.833. Okay. The third root is through this right here. Okay, so it's 3 and 4 is 7, but now we have to add these funny numbers here. So 7 plus, and that comes out to be 7.6666. This will be 14.6666. All right. And then the bottom root is 2 and 5 is 7 plus 7.866 is 14.666. Okay, so I just realized that there's a little bit of an error here, and that is that D was 3, not 4. I used the wrong number in there. So let's recalculate these. So that's 3, not 4. Okay, so the third root down through here, okay, we'd have to do the second root too. So the second root would be 3 plus 3 is 6, is 4 is 10, plus the 3 is 13. So this is 13, not 14. Okay. Then the third root through here would be 3 and 3 is 6 plus this interesting 7.6666, so that's 13 also. It's 13.666. And then the final root is 14.66 because there was no correction there. Just the paths, there are two paths that had D involved with that we miscalculated for. I say we, I did. Okay? Right, so those are the paths. Where's the critical path? Well, the longest path through there, now that we've used these expected values, is the southern path through here. Okay? Great. Okay. So where we're going with that is this is now the expected value. It's a probabilistic outcome here. It's likely that the most expected value that we're going to get there is 14.666 days to get through our network here. That's what we're saying. And the way that we came about that is we had to calculate all those expected values, put them into the network, and then calculate what the critical path was. So just keep reminding yourself that you've used probability. We used that expected value function to come up with some of these times. So that's going to be the expected value of the entire network. Okay. Just to remind ourselves, to get over to the z-score table, we need to use the function z minus x, your point of interest, minus the average over your sigma. So we've got this now. Okay, we're getting there. So we're trying to find the probability now of hitting that day. Now we know that the expected value of the average is 50%. Okay, so here's our data, our normally distributed data. Here's our average of 14.66 days. Okay. So we have to go figure the standard deviation. The way that these problems work is we have to go and calculate the variance. Now they've given us the variance. How does the variance work for all these? Okay. So our equation for variance, which is just sigma squared or standard deviation squared, is what? We're told, and we just have to memorize that, it's the pessimistic view minus the optimistic view. What we're really saying here is how far away is our pessimistic and optimistic? What's the distance there over 6 squared? Okay. And what happens in this problem is we only need to watch the critical path when we calculate these numbers. Now, in the book, you might see that they exhaustively calculate. So we calculated the expected values for each of these, right? We went down there, we got 8 of these. And you could just sit here and just bang out, just knock, 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 get all 8 of them calculated. But a little bit of a shortcut is we're only going to be interested in this critical path for this part of it. So calculating the other 4 is a little extra work. And so on a quiz or an exam or something like that, just remember that it's really this critical path B, E, G, H. It's that critical path that we need to calculate these for. And you can convince yourself of that, or you could just believe me. You can go back to the book and look through there and you can understand where this thing is headed. Okay, so let's do our calculations here. So we need we need to do B is our critical path, E, G, and H, because, just remind ourselves, that was the southern route through here. The B, E, G, H was the critical path. So we only need to calculate variance for those. We have to do it individually to start with, okay? So now we have to calculate these variances. So we need to do B, E, G, and H. Okay, so the variance for B would be 3 minus 1 over 6 squared. 3 minus 1 is 2 over 6, right? So 3 minus 1 is 2 over 6. 2 over 6 squared. Well, is equal to 1/3 squared. So what is 0.333 squared? And that is going to equal, go to the calculator, 0.333 squared is 0.111. Okay, so 0.111. Okay. The next one we calculate is 11 minus 3 over 6 squared is equal to 8 over 6 squared is 1 and 2/6. Okay, so that's 6 goes into 8, 1, and there's 2/6 left over. 2/6 is 1/3. 1.33. Okay, a third is 333. Okay, so we have to square that. One point seven seven six. 1.777. 1.777. The next one is 6 minus 1 over 6 is 5/6. Of course, that's squared. Okay. I have to calculate that. 5 divided by 6 equals, and then square it. 0.6944. And the last one is 5 minus 2 over 6 squared. So 5 minus 2 is 3. 3 over 6. So this is going to equal 0.5 squared. 1/2 squared. Okay, so we have to take 0.5 squared. That gives us the 0.25. Okay, so we have 0.25. Now we have individual variances. These are all the variances, and just like doing the expected value, we're only using the critical path here. We add up these. The nomenclature up here would be the sigma squared of the critical path, right? So we're doing the critical path items. Let's add these numbers up, and that will give us the variance of the critical path. So we're going to add 0.6944. Plus 1.777 plus 0.111 is equal to 2.8324. 2.8324. Now remember, this is the variance. Be very careful here, all right? So to get into that z-score table, we need to use the standard deviation. So we need to take the square root of that. And so if we do take the square root of that, and we get 1.6830. Oh, okay, so 30. It's a 0. Okay. We're almost there. We're about 2/3 of the way through. Okay, so what is the next step? Well, we calculated the expected values, right? So we have the expected value of, we figured out what the critical path was, and so we have the expected value of the critical path was up here. Okay, so we have that. That's our average. And we needed the standard deviation, so we calculated that here, right? And we have, to get into the z-score table, the z-score is equal to your point of interest, which this problem explains to us that it's 16 days. Okay, so what's the probability of getting to the customer in 16 days minus the average, which we figured was 14.66, divided by sigma, which was 1 point whatever it was. What was sigma? Let's come back here. 1.6830, okay? So if you come in here with sigma, that's the standard equation that we're going to use. So the point of interest was, how far away is our point of interest from the mean in terms of, let's compare it to our standard deviation, okay, which was, and again I have to go check a look at what it was, 1.6830, 1.6830, and if we calculate that out, let's come back again to the calculator, 16 minus 14.66 equals, and divide that 1.34 by 1.683. So this is telling us that we're 0.79 standard deviations above the mean. That's what that means. Okay? So if we looked at our data, and it's in a standard normal distribution, rather. There's a normally distributed data here of the likelihood of hitting certain times. Our average was 14.66. We have a 50-50 shot of hitting the midpoint, the average here. But we want to improve our odds of delivering on time. We want the customer to be happy. So we randomly or arbitrarily picked 16 days. We said, we know that we want to pick a time longer than the average. We want to get the odds up. But what if we pick 16 days? What do we get out of that? Like how much increase in probability do we get? That's what we're solving here. So what we do is we take our point of interest, we see how far away we are from the average, this distance here, and we compare it to what the standard deviation was. And the standard deviation was just a little bit more. Okay? It was we figured out that the standard deviation was 1.68, but our distance here was only 1.33. So we're not quite a standard deviation away from the center point here. Good. Okay. So what did we calculate? Did we calculate that yet? I have to go calculate this. Oh, yes, we did. We got 0.7962. Okay, that's the z-score. Keep this straight. We're 0.7962 standard deviations above the midpoint. That's what that equation tells us. Now we can go run back to our table, our fun table here. Let me get rid of this nuisance. Let me delete all that, or just unformat it. So we're going to flood it with nothing. We're going to flood it with no fill. Okay, so I got rid of those colors. They were garish and they were distracting, but they worked when we needed them. Okay, so now we're going to take a look at our table. I'm scrolling up and down. You can see I'm scrolling up and down here, and we have to find over on the left-hand side here 0.79 something above the middle. Okay, so the middle is 0 now. Okay, so we standardized the normal distribution data. And we have to look under 0.79. We come down to the tables. 0.7 here. There's a 0.8. The way this table works is as we go down the page here, we're increasing by 0.1 of a standard deviation, and we've added more precision up here. We've added another, instead of adding a tenth, we can add 100th onto that. We can go out to the 100th place of our z-score. So let's go back. What was that number again? 0.79, we could round up, but let's just use 0.79.8. Okay, so it's funny, but this whole thing rounds to about 0.8 if you just wanted to go to 2 decimal places. Okay, so let's come back into the table again, look up 0.80. Okay, so that would be right here, 0.80, and I am going to remember that one by flooding it so our eyes can adjust and look at this. And it says this is the z-score coming in. This is the probability of that up to and including that number on the normal distribution data. Okay, so what does this say? It says we're pulling out the fact that it's 79%, 0.7881. Let's round it to 0.79 or 79%. There's a Control Z. There's 79% chance of hitting day 16. That's what we just figured out. So try to go over that again if it's not making absolute sense. It really, really, really should start making sense because we're working on a very visceral understanding of what all that we're working on, how it all fits together, and we're looking at the derivation of all of it. It just so happens, it's a complete coincidence that we went in with a number that was the z-score that was 0.79, and we came out with a percentage that was 0.79. That's total circumstance. Doesn't have any bearing on each other. So if for instance, we came in and we said we were 0.4 of a standard deviation above the mean, exactly 0.4, the probability would be 65 or 66%. See that? Okay, so the reading, if we came in with 0.4, it would be 0.6. It's just a coincidence that these numbers right in this area, the number that you come in with the z-score is very similar to the probability that comes out of it. It's just a circumstance. There's no bearing, so don't get confused. And I half assume that they picked these numbers on purpose for these problems, and they wanted us to see that. That just don't get bamboozled. That the fact that you came in with 0.79 or 0.8, and coming out of there we came out with about 0.78. Those numbers are so similar, it's easier to get them confused. And I think they were just trying to do that to us to make sure that we knew what we were talking about. Okay, so that pretty much completes how you would do that one, but we're going to take it one step further. Okay, so this is the first style of the question that says an arbitrary date, an arbitrary duration. What's the probability of taking up to or including that amount of time? The other form of this, it's not any harder, is by picking, in the previous example, by picking 16, we achieved a 79% probability that the number we predict is the number we're going to hit. If you're a company and you're talking to a customer, the customer is going to know pretty much how you're delivering things, and they're going to say, don't you think you ought to give us a better date? Shouldn't you come up with a date that has a higher probability? And to do that, what would you do? By nature, on the spot, you would just go, oh, we'll do it in 17 days, or we would do it in 18 days, or, well, why don't we say, let's go find the number, let's reverse out of this, let's find the number here, the number of days that corresponds to a 99% success rate, okay? And this is a policy. This just says everybody involved with contracts here that's putting out estimates of when we're going to get done, you need to know what we just went through. So why we're going through all this is so you can go do contracts and you can give a finish date on there that is the next step we'll take it to is, let's just say we always pick the number of days that gives us 99% probability that we'd get it done. Okay, so if we do it this previous way, we're just guessing. We're just saying, okay, how about 17? How about 18? And we'd go back to the table and we'd calculate it. Okay, very, very close. There's barely any difference between these problems now. Okay, so let's go back to what the whole z-score business is. It's z is equal to our point of interest. Before we said 16. Okay, so we want to know the point of interest, how far away is it from our mean, and then turn it into relative that distance to how many standard deviations. So that's a generic formula. Now we want to know that when we go into the table, we're going to go get the z-score. We're going to reverse the table. We're using the table backwards. We're going to go to the table here, and we're going to look for 99% chance in here. We're looking for the 99 probability of 99. Now the thing is, in this table you can see how closely spaced some of these numbers get, but let's go find 0.990. Okay, so 0.990 is right about here. Okay, see that? 0.990, and that's, as our z-score would be 2.3 plus 0.03 would be 2.33. Okay, so that's how we do that. We take the percentage and we find the z-score. We're going to come out of the table with the z-score of 2.33. These are the knowns. So we want to find, here's 2.33 is our z-score. that corresponds to 99%. We're trying to find this. Here's our point of interest. Our mean was 14.66 and our standard deviation was, I have to go back to that, 1.6830. So the only number we don't know here is that, so we solve for it. So how do you do that? Multiply both sides by 1.6, etc. Okay, so we're going to end up with 2.33 times 1.683 is equal to x, point of interest that we're interested. Now we have to figure out what that interesting point is, minus 14.66. So the next step is we add 14.66 to both sides, and we have how many days? Okay, so let's try this out. Where do we end up with our calculator? What do we have on there? Nothing useful. 2.33 times 1.683 equals, and then we add it to the mean, which is 14.66. 18.58 days. Okay? 18.58 days. Well, depending on what the contract looks like, usually you're not going to split hairs and talk about 0.58 days. You're going to roll that and tell them 19 days. So in reality, you're going to have you have a safety margin there. You'd have your 99% chance plus a little bit more, like a half a day. Okay, 99 plus something. It'll probably be like 99.2. I have no idea. I'm just guessing. It's going to be something like 99.2%. We'd have to go back in the table and actually figure that out. Okay. In fact, we can. Let's go do that. Okay. So now we're going to go back forward again, and we're going to say our point of interest is 19 minus 14.66. Compare that to 1.683. What's our z-score there? Let's calculate it. 19 minus 14.66 equals, divided by 1.683 equals. So our z-score is 2.57. Let's call it 2.58. We'll round that to 2.58. Going back to our tables here. 2.58. Here's 2.5, and we have to come over to add in the 0.08. Okay, so we have 2.5 plus 0.08 is 2.58, and the probability is 99.5%. We gained half a percent. You know, does that matter or not? I don't know. But instead of just leaving it open, we just weren't lazy. We went and we figured it out. So when we tell them 19, we bought ourselves a 0.5% increase in likelihood. Okay, so hopefully that even that last little example, if you're tracking this here, you're really learning it. You're seeing how this gets used. And what we just went over in here was like a planning table of how to go back to the customer. This is exactly what you would do. You'd end up figuring this out, and you could check off on your success list that you reported your contract, you formed up your contract using the company policy that says you have to have, the minimum is 99% chance of hitting the date. And so you just fulfilled what the company told us to do. Couldn't be easier, right? Well, I hope you hung in there for this. I think this is kind of interesting. It does turn into a game. The more times you do this, the better that you get at it. And that's chapter 6, the learning curve. Okay, it really takes doing this a few times. And for your own good, you could probably take some of these numbers and play around with them, change them a little bit. And it's not that you're going to have an actual number you can compare your answer to, but if you got the steps, if you've got the steps down, you should be able to get through this problem, changing these numbers around and kind of challenging yourself to figure out how these percentages work. And once the lights go on, it's so useful. If you don't push yourself to the point of understanding this, then it's just a bunch of equations. Okay, so I really have put a lot of time into this, I think at least 3 times in class, and then put a full explanation here about how that works, so that you have every chance of like truly understanding this rather than just memorizing it. And then you can add it as a valuable skill, and you can talk to people in your interview and say, I know how to do that. I hope this was beneficial to you, and I hope you do well on the quiz on Monday. Have a good weekend.